first demo, we're going to witness a synthesis reaction. We're going to take a simple piece of copper and we're going to heat it in the presence of oxygen gas to form copper 2 oxide. Note that prior to going into the flame, the copper was shiny, and as it heats up, it will glow red hot, which allows the reaction to proceed forward. Now that the copper is hot enough, watch as it cools down. Examine the color change as it goes from that glowing red hot metal to a cooled down state. The color change that you are witnessing is evidence for something new being formed. In this next demo, we will examine a decomposition reaction. In this reaction, we're taking a sample of copper 2 carbonate, which was the green solid that you saw in the test tube just a second ago. We're going to gently heat that over an open Bunsen burner flame. Please watch at the bottom of the test tube as the reaction takes place. Note the color change from green to black. And as that solid is rising, that's evidence that a gas was being created. Now we're going to take that test tube and we're going to run a splint test to see what kind of gas was generated. Placing an open flame into the mouth of the test tube extinguishes the flame, which indicates to us that carbon dioxide has been produced. The balanced equation for that reaction is written on the board behind the demo. The third demo that you're going to witness is a combustion reaction. It's one that you have seen in class many times. It's the combustion of propane. The balanced equation is written on the board behind the demo. The next demo that we're going to witness is an example of a single replacement reaction. In this reaction, we're going to take a piece of zinc metal and we're going to put it in a solution of silver nitrate. Please note that zinc is a dull gray metal, and also silver nitrate is a clear solution. There are no particles falling off of the zinc metal, and there are no particles actually visible in the silver nitrate. What's happening here is that the zinc is donating its electrons to the solution, and silver is actually coming out of solution as it grabs those extra electrons. You can tell in the video that the zinc is now getting darker, and that's because it is being coated with silver. It's kind of hard to see, so I'm going to pick the piece of zinc up with a pair of tongs and try to tap off some of the silver so you can see it better. All of those pieces that are coming off of that zinc metal are in fact silver that had come out of the solution. Our next demo is an example of a double replacement precipitation reaction. In this reaction, we are going to take a solution of potassium iodide, which if you will note right now, it is a clear, colorless solution, along with a solution of lead 2 nitrate, which is also a clear and colorless solution. And we're going to mix them in the same well plate to see what happens. So potassium iodide plus lead 2 nitrate forms a yellow precipitate. When the nitrate and the iodine switch places or switch their partners with lead and potassium, an insoluble solid is formed. That insoluble solid is lead 2 iodide. That yellow that you're seeing there is lead 2 iodide. This next example is one that is relatively safe to do in front of a class, but I'm going to do it on this demo since I'm not here. I'm adding some phenolphthalein drops to some distilled water just so that we can check for the presence of a base. The next thing I'm going to do is take a small piece of sodium metal, which is highly reactive in water, and I'm going to place that in the water. Please note as the sodium is reacting, it's releasing a gas, which you can kind of see in abundance there. That gas is hydrogen gas. It's also changing the color of the water. Phenolphthalein turns pink in the presence of a base. So what that's indicating to us is that a base is being produced. Sodium turns into sodium plus, and that reacts with the hydroxides from the water, forming sodium hydroxide. The reaction takes quite a bit of time to go to completion, as you have to wait until the metal is completely reacted with the water in order to be safe. Now that the reaction is complete, let's take a look at the equation. This reaction is a good example of a single replacement reaction. We had sodium metal donating electrons into the water. I'm going to write water as HOH to show that water can be written with H as a positive charge and hydroxide as a minus charge. It's another way we can think about this particular reaction. Sodium switches places with that first hydrogen to form sodium hydroxide, which is aqueous. We didn't see any evidence of a solid in the solution. Hydrogen gas was the gas that was released in abundance. To balance the equation, we put a 2 in front of the water, a 2 in front of sodium hydroxide, and a 2 in front of the sodium. In order to carefully dispose of the chemicals that we had in our last reaction, we need to neutralize it. So actually I'm going to show you a neutralization reaction, which is another kind of double replacement reaction. The clear liquid in the beaker is a low concentration of hydrochloric acid. So what we've done essentially is we've mixed hydrochloric acid with sodium hydroxide to neutralize the solution. That solution can now be carefully dumped down the drain. Here's the balanced equation for that reaction that you just witnessed. So again, a neutralization reaction. This is a special form of a double replacement reaction. We started off with our waste product from our other demo of sodium hydroxide, that's aqueous, dissolved in water, plus a solution of hydrochloric acid, again a very dilute concentration of acid. The hydrogen and sodium will switch places, and so one of our products will be sodium chloride, and the other product was water. Again, we can write water as HOH or as H2O.